Hello and welcome to this section of the course. I'm so excited to deliver this section for you. And in this unit, we'll be looking at radians. First of all, we'll dig into the definition of radians and why and how is it used as a unit of measurement for angles. Then we're going to look at arc lengths, area of sectors and segments, solving trigonometric equations in radians, and finally we'll look at small angle approximations. Alright, so let's get to it. Meaning of arc here, the definition of the word arc is the this section of the circumference. So if you're not familiar with the meaning of arc, the meaning of arc, I-A-R-C, is this red, the circumference. The length of this section is the arc length. All right. So if we just look at these three circles here, they're just enlargement of the same circle and the same angle, right? And no matter how big or small the angle is, if you're familiar with enlargement and the scale factor from what you remember from GCSE, the the length of the ratio of these lengths, the ratio of the arc length to the ratio of the radius of the circle remains the same. No matter because the angles here, I said they are exactly the same. All right, so the definition of the radians is, in simple terms, just arc length divided by the radius of the circle. There is a one-to-one relationship for every degree, measured in degree. Then there is a unique ratio that will be angle. So in a lot of equations that are always solved in terms of radians, and they don't use angles in degrees at all. So it's important we understand how and why we drive this radians. So let's look at the ratio of the angle as a uh, total angle around the circle and the arc length. So the ratio of the arc length to the circumference of the circle is exactly the same as that angle divided by 360, because we have 360 in a full turn, right? So starting with this ratio here that I've put in the page, so if we take this fractions and multiply both sides by 2 pi, what we end up with is the arc length over the radius, which is the definition of the radians. So this 2 pi disappears from the denominator on the left and appears on the numerator on the right. And we can do some simplification, because on the right hand side of that fraction we see that there is a 2 on the top of the fraction and a 360. So we can do some simplification. We get the angle in degrees multiplied by pi divided by 180 rather than 360, because we said we simplified this 2 with this 360. So what we see here is the definition of radian. If an angle is measured in radians, it's what it was in degrees multiplied by pi and divided by 180. So from now on, we are going to take this for granted, this formula, and if you're stuck at any point, this uh, this is going to help you out. So my question to you is, what do we do to convert an angle measured in degrees to radians? So what do we do? We're going to take that angle in degrees multiplied by pi and divide by 180. That will turn it into radians. And sometimes you might be asked to calculate the angle from radians, convert it back to degrees. And what do? We, if we rearrange this equation here, multiply both sides by 180 and divide by pi, is the conversion ratio from radians to degrees. Basically, this equation here, this angle is measured in radians, we multiply by 180 and divide by pi. Alright, so let's look at some examples here. We are asked to convert these 60 degrees here into radians. What do? Well, even if you don't have that equation on top of the page, you take 60 degree, you're gonna uh, take the pi, multiply by pi, and divide by 180 degrees. It kind of, well, it simplifies to 1/3 here. So the final answer will be just pi over 3. That's what it is. 90 degree in terms of radians. You can, I'm not sure why they use letter C on top of the angles measured in radians, but that's just the unit that they use. Okay, uh, so let's look at 90 degrees. 90 degree divided by 180 and times by pi simplifies to pi over 2. And if we have to turn angle in radians into degrees, what we're going to do, we are going to divide it by pi and times it by 180. So pi over 4, we said we're going to divide by pi and times it by 180. Now 180 over 160 is 4 times 40 times 4, so that's, I'm taking a guess here, it's 45 degrees. Okay, so pi and, well, I'm actually sure it is 45 degrees because every 1 pi is 180 degrees. If you want to remember that, these two, this is important conversion ratio that you might find useful. 1 pi is 180 degrees, so half a pi is 90 degrees. A sixth of a pi, it means 180 divided by 6, which is going to be 30. Now, if not sure, you can just go through the conversion and see that it will give you 30 degrees. Okay, so some conversion ratios that you might want to remember is 30 degrees as well. So we said 30 degrees is equivalent to pi over 6, and 45 degrees over 4, uh, pi over 3 is 60 degrees, and so on. Okay, so let's look at the next example. We are to uh, convert 7 pi 8 measured in radians, and we want to convert that to degrees. So what we're going to do is we divide by pi and multiply it by 180. Okay, so you take this fraction out of thin air, and that's what you have to do if you're asked to convert between degrees and radians, right? Okay, so you put that in your calculator, and some simplifications will tell you that's 157.5 to 1 decimal place. So in this next example, well, this is just a generalization of some common numbers that you might want to remember for yourself. Okay, so in this part, you should be familiar with this conversion and these particular sine of the and cosine tan of these angles. I've been through this with my year 12 lessons, but if you don't remember, you can think of sine of these angles is going to go up. We're going to start with square of 0. You I would suggest you write square root of 1 over 2, the square root of 2 over 2, the square root of 3 over 2, and here square root of 4 over 2, which is 1. Okay, so these are for sines because sine of the curve will go up as the angle increases. But on the other hand, the cosine of the same angle, it will go down from 0 to 90 degrees. Here would be 0, and when we measuring cosine between 0 and 90 degree, cosine will go down. So it's exactly in the opposite order of what I just described. Add, you will have a square root of 4 over 2 here, which is a 1. Then you'll have a square root of 3 over 2. Then you'll have a square root of 2 over 2. And then you'll have a square root of 1 over 2 and 0 here. So here we said that was a half, that was a square root of 2 over 2, and so on. Okay, and for what do we do for tan? For tan, we will have sine divided by cos because tan is opposite divided by adjacent. So 0 divided by 1 is 0. Half divided by 3 over 2 is 1 over root 3, which can be rationalized as root 3 over 3. That's rationalized. 45 degrees divided is 1. These two uh, exactly the same. That's why tan of 45 degrees is 1. And the tan of 60 degree would be square root of 3. Or these two fractions divided by each other will cancel away, that will cancel away, and you left with square root of 3, and not definite, indefinite. So that goes to infinity. That's not, there's no definition for that. All right. So let's on the next slide. Okay, so the purpose of this slide was to show you that those angles, if you see conversion ratios that are in terms of radians, uh, what those are is, uh, let me just wipe off my handwriting here. So you should be familiar that from now on, if you see sine and cosine of these angles, you should be able to associate them with the right ratios. Okay, with this next examples, we are just looking at these curves here. So it's just to associate for yourself instead of degrees what these angles would be in terms of radians. So every time you see 180, you replace it with a pi, and negative 180 is negative pi. And these are the units of standard units of measurements in trigonometry, and you'll see them again and again. So 270 is 3 pi over 2, and so on and on. Okay, so with this equation, you have to sketch a graph for cos of x plus pi. So this pi, if I jog your memory, inside the bracket, what it does is really it shifts the sine the y and x axis forward by one pi. So what I'm saying is that the curve remains as it is because this is inside the bracket. This it results in effect, and this will shift the y-axis forward by pi. So if you imagine the curve, the red curve will remain as it is, and it will shift the x. The new zero will be here. So if I redraw that curve, that graph view, then the zero angle will be here now, and the curve will be looking something like that. My drawing isn't perfect, obviously, but you should be able to understand that the cos curve with my will remain the same. So this, what it was at pi 3 pi over 2 is really pi over 2 and so on. And when it was, um, yeah, so that uh, this would be pi, and this would be 3 pi over 2, and this point here would be 2 pi, and so on. Okay, so it asks us to resketch the curve between 0 and 2 pi, and that's exactly what I've done above the original curve. Okay, there's a horizontal shift, and the correct answer is also graphically shown to you at the bottom of the page. Just I always suggest to my students to do at least every other question from the book. So there's one thing to watch these videos, and there's another thing to practice it for yourself until it's firmly consolidated in your mind. So happy practicing. I'll see you in the next video.